Welcome to the second video in our comprehensive course on quantum field theory. In the last video, I gave you a brief introduction in understanding the nature of quantum field theory or QFT, approaches in QFT, and an idea on what is called quantization, a very central idea in the realm of field theory. Now, what is the next step? Is it understanding the complex mathematics or understanding the gradual transition from classical to the quantum world? Are the equations of QFT really too difficult to understand? Well, it is easy, simple, fairly methodical, and carries a straightforward path. We will soon explore that in this second video. And my name is Shaunak and you're watching this video on my channel, Physics for Students. Welcome to the second lecture in understanding quantum field theory. In the last video, whatever we talked about is basically a kind of a transition and understanding that what is actually the need for quantization. So we have to understand something which is called a first and a second quantization, and we will start with that in this part of our video. If you have watched the last video, you must have observed that we started with understanding the need for quantization, the basic concept of E equals to h nu, and which addressed the basic idea of ultraviolet catastrophe. We also looked into quantization, which is required because otherwise the energy level of the systems are going upwards and upwards toward infinity, and how this quantization provides stability and answers various questions which were unanswered during the classical era. And typically this is what is called first quantization. So first quantization is basically a framework of traditional quantum mechanics where physical systems are described using wave functions and operators. So it focuses on describing the quantum behavior of individual particles in terms of their positions and momentum. So what we get from first quantization is the general quantum mechanics that we study in the first year or so. This part, which is called first quantization, carries certain important features. Number one is that it deals with particles. So if we have not come to field yet, we are just dealing with individual particles. Second is that the wave function describes the probability amplitude of finding particle in a particular state. The Schrödinger equation, which is very central to first quantization or non-relativistic quantum mechanics, governs the evolution of wave function. And we have seen operators like position with a hat and momentum with another hat are represented as operators acting on the wave function. And all of this actually happens on Hilbert's space, the space of all possible wave functions for a single particle. Now, as you see, we have to change from here. We won't be dealing with Hilbert's space but something else. We won't be dealing with Schrödinger equation, but we have to take something else, and that is what we are basically looking up. So taking a little bit deeper dive into what is called first quantization, we see that first quantization introduced, number one, the wave function, which contains information about the system. It also contains a probabilistic interpretation by squaring the amplitude, which is called the Bosons rule, and obviously the operators describe energy, position, momentum, and so on. So what we can say is that the first quantization replaced the deterministic trajectories that the classical physics tell about into probabilistic descriptions of systems. So it just tells you the likelihood of finding the particle either in this area or that area. It states nothing definite. So the deterministic trajectories are replaced by probabilistic descriptions. However, there were limitations in first quantization which led to the formation of the second quantization. However, the first quantization limitations are few of them. Number one, it was limited to fixed particles. We cannot deal with multiple particles. So particles were treated as the primary objects. Second, what we see is that it could not describe particle creation and annihilation. Example, photons in electromagnetic interactions. and also relativistic effects were only partially incorporated, which we later see in Dirac equation, which itself hinted the birth of quantum field theory. So these were the limitations. However, first quantization is extremely important to understand that how from a deterministic trajectory we came into what is the probabilistic descriptions of systems. From first quantization, we move into what is called the second quantization. So second quantization is the framework of QFT where the focus, as you can see, shifts from individual particles to fields. And here fields themselves are treated as quantized entities. So as we see from moving from particle to fields, this formalism is essential when dealing with systems of many particles or when particles can be created or annihilated. So first what we see is that field operators emerge, like electromagnetic fields are quantized, meaning that they are promoted to operators. There are creation and annihilation operators. These operators describe the addition or removal of particles from a system. For example, this creates a particle, and this is an example which destroys the particle. Also, a Hilbert space that describes states with varying number of particles rather than just a single particle is now called the Fock space. And we are going to look into what is Fock space in much details. And the particles as excitation of fields. Particles as excitation of fields means that they are interpreted as excitations or quanta of their corresponding fields. So what are particles as excitation fields? First, what we see is a multi-particle system. So for first quantization becomes cumbersome for system with many particles. Second quantization simplifies the treatment of such system, especially when the number of particles are not fixed. Second, it comes across creation and annihilation. So first quantization cannot account for process where particles can be created or destroyed. Second quantization is necessary for describing this kind of a phenomena. And obviously, both fields like the electromagnetic field and particles like electrons and photons are treated under one single same framework, making the theory more sturdy and more comprehensive. So this is what is the birth of second quantization, and QFT actually takes up from here. Now, as I have been talking that it requires field operators, creation and annihilation operators, multi-particle system, etc. What is most important are creation of field operators. So promoting the classical field to field operators is something which becomes very important. So as we will see now that how the focus shifts from individual particles to fields, and for that first what we need to understand is that why at all we need an operator in QFT. Why not we deal with single particles as we were doing in quantum mechanics. So first let us understand why do we need an operator in QFT and why it is important. Now, in quantum field theory, operators are very important because they allow us to describe quantum mechanical phenomena in a way that classical fields cannot. What do I mean by that? Specifically, operators provide a mathematical framework to represent quantum states that the process creates or annihilates particles into those states. So first is this, operators provide a mathematical framework which helps to describe these quantum states. The second thing what we see is that, as you can see here, there are creation and annihilation operators. So in QFT, particles can be created, particles can be destroyed, and this process is naturally used by this. Now, this A with a dagger sign right on the top, in general, it can be used in many other areas of mathematics, but you can understand this plus means it is a creation operator, and without a plus means it is an annihilation operator. So, for example, adding a particle to the vacuum state is represented by this. Also, you will see that classical fields are deterministic, and in QFT, as we have seen, fields become operators to account for the uncertainty principle. Hence, once we see this one, phi of xt gets promoted to phi hat of xt, we call this as a quantized field operator. So this is basically a quantized field, and it is no more just a kind of a field. It is a field operator which shifts from classical field to quantum field. So from here what we can say that the role of operator, why it is so important, because they combine the wave-like nature of fields which comes from classical field theory with the particle-like nature of quantum mechanics, and they unify in a single framework. So that is why this becomes extremely important. Now, when we talk of the creation operator, when we talk of annihilation operator, can we take certain examples practically and we see how the equations look like when they follow the relation? So first you see that bosons, example photons, they follow a commutation relation. Now, what we mean by commutation, I will come to that, but first let us have a look into this equation. And I'm just going to decipher this equation part by part so that you can understand. And then you will understand why and what is the importance of operator in QFT. So first you can see obviously this is an annihilation operator. That means it removes a boson from mode K. This comma is basically what is called a commutator. And the commutator ensures that the operators are compatible with symmetric wave functions. The second thing is that obviously it is a creation operator because it has got a dagger sign on the top and it adds a boson. Again, this AK, the K which we are talking about, is basically referring to specific energy or momentum state of the field. And this Kronecker delta, meaning that the commutator is non-zero. We will look into this commutator later. So from here, what we can understand is that a boson follows the Bose-Einstein statistics, and hence you can see that the wave functions are symmetric in nature. So phi of x1, x2 is equals to phi of x2, x1. So ultimately the bottom line is that the operators actually allows us to enforce the proper statistics. For example, here we see Bose-Einstein statistics which follows with bosons, and in order to write the statistics we need operators that create, then annihilate, the commutation and the Kronecker delta and so on. So this is a classical example of why do we need an operator with the bosons, how the commutation relations are followed. Now, what if the commutation relation is not followed? And we find these are called fermions, and the equation looks more or less like this. You already know some part of it. This is an annihilation operator. This is again an anti-commutator which enforces anti-symmetric wave function. Remember, because this is an anti-commutation relation, so the commutator has to be anti-commutating. Why? Because these are fermions not obeying the Bose-Einstein statistics. We will soon see that what do I mean by fermions in here. So again, this is a creation operator which adds it, and fermions actually follow Fermi-Dirac statistics, which means it is anti-symmetric, and as you can see in this equation, there is a minus sign. So minus sign means that it basically follows what is called the Pauli exclusion principle. That means no two fermions or subatomic particles actually have the same quantum state. It is exactly the opposite of Bose-Einstein statistics. Now you might have a question that why it is so. Why it is that it has got a Pauli exclusion principle, and why it is that things are not happening in this way. Now, in order to do that, I need to go a little bit in making you understand why this difference is in terms of commutator relationship. So as you can see here, this is the commutation and this is the anti-commutation relationship. So what we can see over here that the difference in commutation and anti-commutation relation arises because bosons and fermions obey different quantum statistics, and this is due to the intrinsic spin. This is not a part of today's video. However, I would just like to tell that this is something which is related to intrinsic spin, and from here what you can see that integer spin follows Bose-Einstein statistics, hence they are symmetric in nature. Fermions follow half integer spin, they follow Fermi-Dirac statistics, and hence they are anti-symmetric states or anti-symmetric in nature. So remember that the distinction deeply lies to the spin statistics theorem, which is a result of quantum field theory and special relativity, which we are not covering over here. So the commutator relation actually allows the multiple particles in the same state, and the equation goes something like this. And what does it tell? It tells that bosons exhibit behaviors like Bose-Einstein condensate, where all particles can occupy the same lowest energy state. So Bose-Einstein condensate, if you see practically, it is a very, very cold state. And when cold state means that things are actually occupying together. They are staying together in a very close bond. And that is why it follows the things together at the lowest energy state. On the other hand, this actually is the anti-commutator relation. And it enforces the Pauli exclusion principle, which says that these things cannot stay together. And they prevent actually more than one fermion occupying the same state. Now, you question yourself that can you explain all of this without operators? These are all operators which are taking place here. So why do we need an operator in QFT? The answer is very clear. The boson, the fermion, the statistics, how do we explain without having operators? So here is a summary table which will help you to understand the properties of bosons and fermions. So the operator relation is this, which you can understand from the mathematics. Wave function symmetry, this is symmetric in nature. This is anti-symmetric in nature. Statistic wise, it is Bose-Einstein, and the second one is Fermi-Dirac statistics. And examples of bosons are very simple. Photons, gluons, Higgs bosons, and fermions are electrons, protons, and neutrons. Now, as I was telling that why does it matter, why it will happen that they follow the Pauli exclusion principle, this is not. And this is because operators essential, without them such a description would not be possible. Now, in order to give you a pictorial understanding of bosons and fermions, if you see this to be a boson, now you can see they are piling up on one another. They're just piling up on one another. So that is why we call that it allows particles to pile up on one another and the other and in the same state. And you have already seen what is the example. This is the example of gluons and photons and so on. On the other hand, if I see the fermions, these are fermions, you see, they are keeping a safe distance. That means these are actually not occupying the same state. And as you can see, fermions actually are the building blocks of matter. So they form the electrons, protons, and neutrons and give rise to the structure of atoms, molecules, and solids due to the Pauli exclusion principle. So, by introducing commutation and anti-commutation relationship, quantum field theory provides a consistent mathematical framework to describe these two fundamentally different types of particles, how they behave. So I hope till now you have got an understanding that why do we need an operator, just as we need fields, how it gets promoted to QFT, and the extremely important part of operator in order to describe what we call these particles, why they're different, and how do we do the mathematics with the operator. Now, this is why we need the operator, but yet we have not understood what is a field operator. Now, in this part of the video, I will give you a very simple yet a mathematical understanding of what is a field operator coming up into the next part of our video. Now, in classical field theory, if I take this phi of xt, it means that it is a scalar field and it is a function that assigns a scalar value at every point in space-time. For example, you can think this to be an abstract space-time, and all these arrows are telling that they assign a scalar value at every point. For example, I can take that classical theory. In classical theory, the field is continuous, but in QFT, the field is quantized. Hence, assigning a scalar at every point won't be possible. Right? And particles correspond to the excitations of the field. But before going into that, when we say that it assigns a scalar at every point in space-time, let us take an example. Very simple. From the classical mechanics, we get A is the amplitude, K is the wave number, and omega being what is called the angular frequency, T being the time. So what does it represent? Very simple. This represents a plane wave moving in space-time. This is a simple example. Now, you will see that how this simple mathematical equation becomes a little bit bigger the moment we insert QFT. So, the field values of phi xt gives the field value at a space-time point of x comma t. Quantum field theory, when we use it as an operator, acts on the quantum state of the field. So in particles in classical theory, field is continuous, so that is why we can denote every space-time point. And in quantum theory, because the field is quantized, particles like photons or scalar particles correspond to what is called the excitation of the field. Now, as I was telling you, this phi xt, once I take it into operator, the equation looks a little bit bigger than this. Yeah, this is how the equation is, but don't worry, I will just explain you very simple. You already know, as you can see, a little bit introspect into this equation. Some part are already there from the classical theorem. So what we can see over here is that this phi with a hat of xt, this is the quantum field, and it is basically the field operator, and it is a scalar field that varies smoothly over space and time. So because it is quantized, so it becomes an operator which acts on quantum state. So what does it describe? It describes the value of the quantum field at a position x at time t, and the possibility of creating and annihilating particles. We next go to this. This is an integral which integrates all the possible momentum modes starting from kx, ky and kz. This d cube k by 2 pi cube. This is what we called is the ensure that it ensures basically what is called a proper normalization. A proper normalization, I hope you understand what is normalization. So the integral here actually sums over all possible wave vectors k corresponding to different momentum modes, and the 2 pi cube ensures proper normalization. If we take this factor, this is basically the energy of a mode k in natural relativistic dispersion, and this is the normalization factor which shows omega k equals to this much. So this is basically what we call is the energy of a mode k. Now here you see this is something really wonderful coming up. This is something which we already seen in static plane waves. This is thus the complex conjugate, and is actually tells a wave forward moving in time with momentum k. This is the creation operator, and this is something which tells a wave moving backward in time, or I would say in opposite direction of the complex conjugate at the first term. And I have not missed the annihilation operator, which is over here. So you see that this is basically what the equation looks like when we take it into the QFT operator. So as I was telling you, 1 upon a square root of 2 omega k, this is representing the relativistic energy. So the factor to 1 upon 2 omega k ensures proper normalization of the quantum field, ensuring that the Hamiltonian, that means the total energy, the kinetic and potential of the system matches with the physical energy. This was how things look like. Now I have to take two things from this equation into the next page, and I will show you. Now this term actually represents a wave traveling in time with momentum k and energy omega k, and it would look like this. Its complex conjugate, which has got a -1, mathematically corresponds to a wave that propagates in the opposite direction in the phase space, and which can be interpreted in some context as moving backwards in time, and it looks something like this. The arrow is on the opposite direction. So what do we understand from here? What we understand that the field operator phi of xt, which was earlier just a kind of a field, now it has become an operator when we put a hat, actually has two terms. Number one is this one with the annihilation operator and destroys a particle of momentum k, and this one. So here you can see this is an annihilation operator, this has got a creation operator. So automatically phi of xt gets promoted as an operator, and it shows two parts. The annihilation operator, the creation operator. That means for antiparticles. And this combination actually, what does it do is that it ensures that the field captures the entire complete full dynamics of particles and antiparticles consistently with quantum mechanics and special theory of relativity. Now when we say this minus, you might question that why does this arise? And this arises because relativistic wave equations admits that positive energy and negative energy solutions. So if you go into Dirac equation, and if you go to my videos on physics for students on Dirac equation, you will see that there is a negative energy. And during that time, there's a negative energy. Dirac thought that it is something wrong, but this actually accounts into negative energy solutions. So Dirac equation also does this, and here also you can see. So ultimately the bottom line is that this is what is called a field operator, and it actually has two components, and I showed you the details. So can we summarize from here? I mean to say, can we summarize what is a field operator after looking onto all those mind-boggling equations? So the first thing is that why promote classical fields to quantum operators? Because classical fields cannot account for particle creation and annihilation or the probabilistic nature of quantum mechanics, and quantum operators introduce a framework in order to handle discrete particle-like behavior. What are the key differences between classical and quantum field? Here you can see that classical field is continuous. Quantum field is a mathematical entity acting on a Fock space, we will see, allowing the description of particles and their interaction. There is a transition, obviously, from classical to quantum. There are certain steps. I'm just giving you a summary. You need to select a classical field, decompose it into Fourier modes, replace with mode amplitudes, and then impose the commutation and anti-commutation relation, for example, for bosons and fermions. What quantum operators actually get? What does it achieve? Yes, it achieves particle creation and annihilation. It gets quantized energy level, for example, E equals to h nu or E equals to h omega k. And the Fock space, the quantum field, acts on a Fock space, but the number of particles can vary. And obviously the commutation and anti-commutation relations remains over here. The first one is the boson with integer spin, and the second one is the fermion, which is called the half integer spin. So from here, what we can say is this one: promoting classical fields to quantum operators is essential to describe the quantum nature of particles and fields. And this actually enables the phenomena in order to describe what we call interactions, creation and annihilation, all of them in a nice single framework, and which is mathematically consistent. So here we have finally arrived at the conclusion that why do we need field operators and what are field operators. Now, as I have been telling you that we need to learn something which is called a Fock space, and in the next part of the video I'm going to explain you what is a Fock space. Now the picture, the person that you can see on the screen, Vladimir Alexandrovich Fock. He was born in St. Petersburg, a very influential mathematical physicist, did foundational works on quantum mechanics and quantum electrodynamics, also made important contributions in general theory of relativity, but in 1932 he wrote this paper, Configuration Space and Second Quantization, and is famous for that, and here he propounded an idea which is called a Fock space. The general idea of what is a Fock space is basically it extends the Hilbert space to describe multiple particles. Now my question is that, as I have told you, what were the limitations of Hilbert space? Because in order to have a mathematical or a physical theory, we need to understand the limitations or problems of a particular space which will give rise to another space. So what were the limitations of Hilbert space that gave rise to Fock space? Let us understand that first. So Hilbert space and its limitation. Named after the famous German mathematician, influential mathematician I should say, David Hilbert, Hilbert space is basically a mathematical space which is used in quantum mechanics to describe quantum system. I'm not going to define mathematically what is a Hilbert space, which I will do into the later part of the video. So from here what we can understand is this, that if we take the state vectors, for example, which is a single particle, Hilbert space, the space of all possible wave functions for that particle. And if I take Hilbert space as the tensor product, then it describes a combination of two particles. As simple as that. Now, if I take a particle which is of a single dimension, say for example, if I take a particle which is of one dimension, we get an equation like this. Now hold on, I'm just going to tell you what this equation means. So if I take this part, this is basically what we call is the state. Now if I take the integral, it actually sums over all the possible values of x. The psi x, this is the wave function, this is the basis state, and this represents, we will see, very small infinitesimal increment of variable x. The question is that physically, what does this equation tell? I mean to say, I just explained to you a very simple way, but what does this equation tell? Carrying on with the same equation, I would like to say that the equation represents how a quantum state, which is this psi, is an abstract Hilbert space, can be decomposed into a superposition of the position eigenstate, which is this one. So the wave function, as we see, This one, okay, let me explain to you the dx part. So, okay, remember that the wave function psi x encodes all the probabilities and amplitudes which can be associated with the particle. So, if I take now the dx, you can think of this dx as a tiny piece of continuum or a small slice or segment which is summed over. And you can think is something like this. The typical discrete one, ai, is summed over all the discrete values of I. In a continuous system, dx allows you to sum over an infinite number of infinitesimal small slices. This is very important. So as you can see on the left hand side, sigma, as it sums over all the discrete values of I, dx allows you to sum over an infinite number of infinitesimal small slices. So from here, what we can see is that this one actually tells what? It is made up of many small pieces where each piece corresponds to the system. And psi x actually, so remember the first one, this one is made up of many pieces and each piece corresponds to the system being at a specific position. Psi x is a wave function. That means, for example, which tells us more or less where the system can be found at x. This one, the basis states describe the system being exactly at a certain position, and the integral actually adds or combines all the contribution from the states to form the complete quantum state, which is the vertical bar followed by a psi followed by an r angle. So this is what the equation tells, and this equation is where? On Hilbert space. This is what? One single dimension equation. Now, this equation also has got a relation to a Hilbert space, obviously. What is that relation? Number one is that it actually lives in Hilbert space, which is an abstract infinite dimensional space where entire mathematics of quantum physics is defined. This is what is called a part of basis in Hilbert space, meaning that any state can be expressed as a combination of these basis states. The psi of x, we know, acts a kind of a, we can say coordinates, not coordinates, yeah, we can call it coordinates or components of the state vector of this space. Now we come, so this is the, actually if you go back, now you see this part is basically what the equation tells. This part actually tells what the equation actually tells in relation to Hilbert space. And now we come, what are the limitations of Hilbert space? So if you talk of the limitation, the first is that it can only describe a fixed number of particles. So that is why the tensor product. The second one, it says that obviously it cannot describe any particle creation or annihilation, obviously. The second one is that non-uniform dimensionality. That means multi-particle system obviously requires combining separate Hilbert spaces, leading to complex bookkeeping. For example, two particles system uses tensor product of two single Hilbert spaces and so on. So that it is lacking. The lack of vacuum representation, obviously the vacuum state into a fixed number of Hilbert space framework as it requires space that includes all particle configuration. The symmetry constraints also, Hilbert space must enforce symmetrization or anti-symmetrization for fermions in order to ensure compliance with quantum statistics. That is also something which is missing. And lastly, we say scalability factors. That mean field quantization involves sometimes infinite degrees of freedom, which a single Hilbert space cannot handle effectively. And that is why we need a new space which is called the Fockspace, which naturally incorporates this infinite modes. So we understood the single dimension relation, we understood this relation to Hilbert space, and we also understood what are the limitations of Hilbert space, which led to the new space which is called the Fock space. So in this part of the video, I will give you a very clear mathematical and a simple understanding of what is a Fock space. So if you can read the definition, it is nothing but it is to describe system with variable number of particles. So when we move from fixed number of particles to variable number of particles, we get, fixed number of particles means H1, which is a traditional Hilbert space. When it moves into variable number of particles, we get an equation something like this. Let us look into the components. First is the Fock F, which represents the Fock space. Remember, this is also a Hilbert space used to describe quantum state with a variable or infinite number of particles. This one is the direct sum, and we will soon see what this direct sum means. It actually means combining multiple vector spaces into one big large space. Now, next thing which comes is n equals to 0. This term corresponds to the vacuum state, and this Hn is the Hilbert space described with n particle state. So, as I told you that this is a sum over of all the different multiple vector spaces. So, the fockspace F can be written as the direct sum of H0, H1, H2 and so on. Here H0 represents the vacuum state, H1 is the Hilbert space for single particle, H2 is a Hilbert space with two particles, and so on and so on. Now, in order to understand or get a kind of a schematic diagram understanding of what these Hilbert spaces add up to, I would like to show you a nice diagram. Now, as you can see, this is the direct sum, and this Hn is the layers of Fock space. You can imagine this to be a layer. And the first layer has no particles, vacuum. Second layer has one particle. Third layer has two particles, and it goes on and on and on. And together, once we sum up this, it gives you the complete Hilbert space, which is the F. And this enables what? The description of any quantum state with any arbitrary number of particles. Now, why it is so important? Because number one, it allows variable number of particles, which is very crucial in quantum fields, right? And the second part is that it also allows for a variable number of particles and enabling the description of a quantum state with any arbitrary number of particles. So one is the variable number of particles, another is the direct sum ensures that the states with different particles are orthogonal to each other. So this is the importance, a very important factor, how we define those Fock space, and ultimately it is completing layer by layer and giving you the complete Hilbert space. So this is again the definition of the Fock space. So the Fock space can contain vacuum state, this one which represents the absence of particles, and as we see that it builds up with this one. Now, so it builds up as a direct sum. That means bosons, for examples, each n particles is symmetrized or anti-symmetrized in Hilbert space. So bosons are symmetrized states, fermions are anti-symmetrized states, and as I told you, the states in Fock space can be written as n1, n2, so on up to ni. And it also includes a creation and an annihilation operator. And also Fock space can be written as an inner product, which makes the equation looks like this. So once we say that they satisfy the commutation and anti-commutation relation, I would like to show you what do I mean by this. So here you can see the equation commutation, anti-commutation, bosons, commutation, anti-commutation, fermions, and these are actually used a lot in quantum field theory in order to describe photons, electrons or other quanta. So Fock space is nothing all related to theoretical things. It handles also a system where the particles can vary, for example, for creation and annihilation process, typically for quantum optics where we are using laser lights, etc., and many body physics where the Bose-Einstein condensate or fermionic systems are written. So Fock state of n particles can be represented as this multiplied by this and so on, where C sub n are coefficients and this phi I are single particle states. Now, as we have got operators in quantum field theory, we have seen why it is important, what are the operators in quantum field theory. Similarly, we have operators in Fock space, and these operators actually play a good amount of a significant role in quantum field theory. Let us look into the operators in Fock space. So Fock space actually introduces creation and annihilation operator, which you have already seen, and it also includes what is this one. It is called a vacuum annihilation operator. That means it actually doesn't, you cannot remove a particle from the vacuum. So the creation operator means it adds a particle to the system. And here you can see this is what I was talking about, that this is a commutation relation where this is the annihilation and creation operator and this is Kronecker delta. Remember, at the beginning of the video, I told you that we will look into this. This is the time that we should explain the Kronecker delta. Those who have taken up a course in tensor analysis, you already know that Kronecker delta is actually represented by this. So it ensures that the commutation relation is non-zero when the modes of k and k prime are the same. Now, question is that what does the commutator mean physically? I mean to say there should be a meaning. So there will be two things that I would be taking. One is when k equals to k prime and when k is not equals to k prime. So here you can see, first I would take when k equals to k prime. And when I say that when I say k equals to k prime, the commutator relation will be something like this. It will be equal to 1. So what do I mean by this? When we in classical physics, as you know, that observables such as position and momentum are just numbers and they commute. That means if you have two quantities A and B right on the screen, their order of measurement does not matter. So this really does not matter. AB equals to BA. Similarly, creation and annihilation process in classical system don't involve discrete steps. Energy can be added or removed continuously. Why? Because the order really doesn't matter. Now, when we take the operators, often they do not commute. They do not commute. So if they are not commuting, that means the order really matters. So these operators do not commute, meaning their orders matter. And these are responsible for finding and removing a quanta. So what we can see here is equals to 1. That means it ensures that the process happens in discrete individual steps. So the creation and annihilation operators are responsible for adding and removing quanta. Their commutator, this equals to 1, means that the process happens in discrete individual steps. When k equals to k prime, it is equals to 1. That means it is not commutating. If it is not commutating, that means the order matters. And why the order matters? Because it is happening in discrete individual steps, not unlike classical physics where things takes place in infinite smooth way. So we take the next part of is when k is equal to, not equal to k prime. Here we have seen k equals to k prime. When k is not equals to k prime, we get that it indicates that the annihilation operators for different modes commute. Here it actually commutes. Now what do we mean by this is that creation or annihilation operators have correspond to different modes and their commutator is actually 0. Now, when we see that it reflects in independence between the two modes, that means creation and annihilation operator in one mode, k, has absolutely no effect on the creation or annihilation of quanta in another mode, which is k prime. So when I talked about independence between modes, independence means what? One person is independent of another. That means there is no effect. Here also, if you're using creator or annihilation in one mode k, it won't be creating any kind of a difference in another mode k prime. That is why k is not equal to k prime and the value is equal to 0. So physical excitations in one mode really do not influence anything other. So what is the key takeaway? Now let us look into the key takeaway. When we say that this commutator for k is not equal to k prime, it ensures that the modes are independent subsystem. The creation and the alienation of quanta in one mode has got absolutely no influence in other, and this is the cornerstone of the formalism of what is called the multi-mode quantum system. So these are the operators which play a very, very vital role in Fockspace. Now we have been talking about Hilbertspace and Fockspace. Are there any relation, or we should say a kind of a difference between Hilbertspace and Fockspace? Let us look into the next part of our video. So if I go by the definition, you already know that it is a complete vector space but deals with fixed particle system, and this can go up to varying particle system. Mathematical structure, this is a single vector space, and this one is F, which sums up the n particle Hilbert space. The application wise, if you see it used for system with fixed particle of degrees of freedom, and this one used for variable particle freedom. So obviously the definition wise, mathematical structure wise, and application wise, you see there's a difference. The most important difference is the key operators. Here the operators are observables. These are creation and annihilation operators. And the key commutating relation, here no typically used, and here as you can see boson and fermions. The applications part is that quantum mechanics for single particles, and here quantum field theory for second quantization. So Bose-Einstein condensates and any other fermionic system are better defined in Fock space. So that's it for today's video. It has been a little bit long, detailed, mathematical, intense, but I hope that this second lecture has been useful. We dealt with what is an Hilbert space, what is a Fock space, why do we need field operators, what is first and second quantization, and so on. So thank you very much for watching this video. If you have liked the video, please do subscribe to my channel Physics for Students, and do not forget to click on the bell icon to get all the notification from Physics for Students. You can also contact me at this email ID and subscribe to my other channel exclusive to General Theory of Relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with more videos, but I hope you liked it, and let me know your comments and reactions in the comment box. I will be soon back, but till then, may the good Lord be with you.